5, recurrence relation for merge sort. We need to do analysis. We need to estimate the efficiency for the worst case. The reason is we want to see if the worst case is good or not. Because our goal, we want to avoid poor worst case performance. All right. Let's look at how do we derive recurrence relation. To estimate worst case efficiency, so let us start with this general situation. So we use this t function, t of n, to represent the number of comparisons to sort the whole array using the merge sort. Okay? Then we do divide and conquer with even split. So we get 2 subarrays, each one approximately half of the size, n over 2, t of n over 2. Okay. But we have a merge step. The merge step approximately n comparison. So why approximately? Remember the total number of elements minus 1. It should be n minus 1. But here, because we want to make our equation as simple as possible, so we drop that minus 1 part. All right, so with this simple analysis, now we are ready. We can write out the recurrence relation. That's this. Base cases, 2 base cases, when there is 1 element, no comparison, t of a equals 0. When there are 2 elements, 1 comparison. After that, we use this recurrence relation. T of n equals 2 times t of n over 2 plus n. All right. Then how to solve it? The next question is how to solve this recurrence relation. So here, we still use some method we used before. Consider a simpler case. What is the simpler case? Look at this part, n over 2. N over 2 could cause some problem. When n is even, when n is odd, there is some, complexity we need to deal with. So to avoid that complexity, we like to make n power of 2. 2 to the k, power of 2. In that case, we do not need to worry about n over 2 situation. Okay? Yeah. All right, so let us use n equals 2 to the kth power to simplify the original recurrence relation. What can we get? So we plug in, we get this new recurrence relation. Next step, how do we do the transformation to expose its structure? We need to solve it. But if we cannot expose its structure, it is not easy to solve. So the next step, we want to do transformation here using division method. Division method. Why division method? Why division method? Yeah. All right. So I do division. So this equation divided by 2 to the kth, both sides of the equation. Divided by 2 to the kth, both sides of the equation. Yeah. So you may wonder, so how do you know you should do division in this situation? How do you know? Right? Yeah. Although based on experience, but another thing is, we want to get similar structures, both sides. Similar structures, both sides. Yeah. We have the similar situation in the Tower of Hanoi problem. Tower of Hanoi problem, C of n equals 2C of n minus 1 plus 1. In that one, we plus 1 both sides. In that case, we try to get a similar structure both sides. Here, we try to explore, try to get a similar structures both sides, but in the structure like this, we have to use the division method. Okay, yeah. All right. After that, in order to get a better view of the equation, we like to define a new function. Yeah. So this new function try to simplify the old function to give us a better view. Yeah. So the new function is this. Yeah. So this fraction, this part, we use a new function g of k. So to make it look simpler, okay, g of k, yeah, it's a simple function. Yeah. T of 2 to the kth over 2 to the kth. Okay. After this simplification, yeah, we do substitution method. Yeah, I mean, we simplify the original recurrence equation. Yeah. The new equation as simple as this. G of k equals g of k minus 1 plus 1. That's very simple, right? Yeah. All right. And we know g of 1 equals 1/2. Yeah, why 1/2? You may ask me, why 1/2? You plug in k equals 1, yeah, equals t of 2 over 2, right? But t of 2 equals 1. So that's why 1/2. Okay. Now we do another iteration, g of k minus 2 plus 2. Because 1 plus 1, yeah, 1 plus 1, yeah, 2. And we keep doing this, yeah, all the way down to the bottom. But how do we keep track of all these equations? How do we keep track of them? Invariant. Invariant. I used this method many times before. Invariant. What's the invariant? The size number here, k minus 1, k minus 2, size number plus the constant term, its corresponding constant term equals k. That's the invariant. Okay, never changes from top to bottom. When we reach the bottom, the size number is 1, then the constant term part, k minus 1. So we won't get lost. When we use the invariant to keep track of the, relationship between size and a constant term, we will never get lost. Okay? Yeah. All right. So with this last expression, we plug in g of 1 equals 1/2, we get g of k equals k minus 1/2. K minus 1/2. All right. Then we can write t of 2 to the kth equals, parenthesis, k minus 1/2. Whole thing multiply 2 to the kth. Okay? Yeah. We can write it back to n expression in terms of n. Yeah. K equals log n. Okay? Yeah. So we can write t of n approximately n times log n. Yeah. Because this 1/2 can be dropped, right? Too small, too little. Yeah. Not important. We can drop it. So k times 2 to the k, so n times log n. Yeah. But remember, that's only true for n equals power of 2. If n is not equal to power of 2, for the general case, is it still true, the general case? Answer is yes, but we need to do some work. For the general case, why this is still true, we can we can answer that question, but we need to do some work to get it. Okay, yeah. There are two ways to get there. Yeah. The first way, next video I will talk about recursion tree. Recursion tree method. We did that before. Remember the recursion tree? 3-element partition, 5-element partition. We use that to solve selection problem. We use a recursion tree there. Okay, selection problem. Okay, yeah, that's one method. Another method, we also use that before. Yeah, we also used that before. The binary bits problem. Binary bits problem. Remember, smoothness rule. Smoothness rule. Sorry. Smoothness rule. We can also get that. Two methods. All right. In our last video, D.6, we will use these two methods to get the answer. All right, so let me stop here. Yeah.